Hello, everyone, and welcome to the webinar. My name is Bill Calver. I'm the director of the AcuSolve program management team, and I'm here to introduce you to some exciting new features that are available in AcuSolve 2022. So let's get started. In this latest release of AcuSolve, we bring you two new powerful multi-phase features. An integrated electric potential solver, some changes to our documentation and its structure, as well as some general enhancements. Now, AcuSolve began the journey into multi-phase with our level set feature for immiscible flows. We then expanded into dispersed multi-phase with algebraic Eulerian and to Eulerian Lagrangian granular flow with AcuSolve EDEM coupling. Now, Altair AcuSolve continues the investment into dispersed multi-phase with the release of the Eulerian multi-phase model and the Eulerian granular multi-phase model. So let me get into a little more detail on each of those topics. As the backbone to AcuSolve EDEM coupling, it's only natural that we would release the Euler-Euler model as its own feature. This model is the most comprehensive multi-phase model where mass and momentum are conserved for each phase, and exchanges in momentum between the individual fields and the carrier field are fully accounted for. Each phase is treated as an interpenetrating continuum where the particles are not tracked individually, but rather modeled as an ensemble averaged cloud. Dispersed materials can be any type, liquid, solid, gas, because each phase is tracked separately by its own momentum equation. The velocity of each phase can be defined separately at inlets for any of the non-pressure inflow types. It also allows for the output of specific dispersed field velocity. And finally, it provides the foundation for further multi-phase capabilities. So what does this get us? The new Euler-Euler multi-phase feature delivers more fidelity than the algebraic Eulerian model with the calculation of the specific phasic velocity fields, more accuracy because we're now tracking the momentum exchange between individual dispersed fields and the carrier, and not just calculating a single mixture velocity field, and more detail in the solution because more intricate models of phase interaction are provided. Now, with this new feature, we include the field flux volume fraction quantity for each field. And when integrated on a surface, this is basically a fancy name for mass flux of that particular field. In the SimLab interface, to AcuSolve or to access Euler-Euler multi-phase, users will create a transient flow solution, then activate multi-phase flow type Eulerian. Gravity is automatically activated for transient multi-phase, and users should be sure to check the direction. In the material definition, users can either define or identify a fluid material for both the carrier and the dispersed phase fields. Multi-phase material is created to associate the carrier fluid with the dispersed fluid, and up to 5 dispersed phases can be defined for each carrier fluid. At the inflow boundaries, the volume fraction of each phase and the carrier must be specified. As I mentioned earlier, Euler-Euler multi-phase allows the user to set specific velocities for each of the dispersed phase. This is known as phasic velocity. Information can be specified on velocity, average velocity, mass flow rate, or volume flow rate in flow boundary conditions. In the HyperWorks CFD interface, the user activates multi-phase flow and sets the type to Eulerian. The alt Eulerian material of water, oil, Eulerian is then populated. With the selection of multi-phase flow, the simulation type is automatically set to transient, and gravity is automatically activated. Again, in order to check the direction of the gravity. In the materials database, users can create new fluid materials if necessary, and create a new Eulerian multi-phase model to, again, associate the carrier and the dispersed field if the default is not sufficient. HyperWorks CFD supports one dispersed phase for the carrier fluid. At inflow boundaries, only the volume fraction of the carrier fluid needs to be specified in HyperWorks CFD. The dispersed phase volume fraction is taken as 1 minus the volume fraction of the carrier. And phasic inflow can be specified, again, with any of the 4 inlet types shown here: velocity, average velocity, mass flow rate, and volumetric flow rate. As I mentioned earlier, Euler-Euler multiphase is the most accurate approach for multi-phase scenarios, but there is an additional 10 to 20% compute cost due to the extra solve of momentum and continuity for each of the dispersed phases. This table kind of highlights some of the differences between Euler-Euler and algebraic Eulerian, but the guidelines that you should use are that you should use multiphase Euler-Euler multiphase when the carrier fluid is lighter than the dispersed fields, when the different phasic velocities are needed at inflows, and when the accuracy of the solution outweighs the importance of cost. So in summary, the new Euler-Euler multiphase model allows for more detailed multi-phase simulations by calculating momentum and continuity of every active phase. It provides more fidelity and accuracy than the algebraic Eulerian mixture model, and more phase interaction detail with additional mathematical models. These additional models are particularly useful in bubbly flow scenarios. The comprehensiveness of Euler-Euler is really demonstrated when the volume fraction of a phase reaches 1, and it essentially behaves like an immiscible fluid. In version 2022, users have access to Euler-Euler multiphase in SimLab and HyperWorks CFD. So based on the Euler-Euler multiphase feature, and actually an extension of it, is granular multiphase. I mentioned before that the solid dispersed phases could be used with Euler-Euler. When the volume fraction of those particles becomes high, say about 20% or more, additional physics need to kick in. This is what's included in the granular multiphase feature. So it's important to note that we're modeling dispersed solids. Even at higher volume fractions, we're not tracking individual particles, but rather a continuum. The particles in this continuum are assumed to be spherical or nearly spherical. The new physics that come with the granular multiphase feature include new drag models for dense phase flow. We've actually had the Gittesbow drag model from previous releases, but the EMMS is a new addition, and both of these models are appropriate for dense flow. Granular temperature, which is a measure of the random energy of a particle, can be thought of as similar to the turbulent kinetic energy in a turbulence model. The solid pressure and viscosity, which are needed to accurately model the behavior of the densely packed granular regions, and a few parameters related to particle collisions. In SimLab, a user will begin a granular multiphase solution setup the same way they would for Euler-Euler multiphase, including selecting multiphase type Eulerian. However, when a solid material is specified as one of the dispersed phases, the granular properties section of the material definition will be made visible, and granular multiphase will automatically be activated. It's worth noting that granular multiphase is applicable even when the volume fractions of a solid dispersed phase is low. So activating it when your volume fractions are below 20% there's no negative effect of that. Again, up to 5 dispersed phases can be defined. Specifying inflow volume fractions and phasic velocities for granular flow are no different than with Euler-Euler multiphase. In the HyperWorks CFD interface, to simulate granular flow, the process is a little bit different. The user should select the multi-fluid type granular. Similar to the Euler-Euler multiphase workflow in HyperWorks CFD, the default material is populated, this time for a granular material. A new material can be defined. When defining a new granular multiphase field, the granular properties section will automatically be shown. And as with Euler-Euler multiphase in HyperWorks CFD, currently undispersed granular field can be defined. Inflow conditions are specified in the same way as Euler-Euler multiphase for safety. So another question you might have is granular multiphase. How does that compare to AcuSolve EDEM coupling? Well, the two complement each other by only overlapping in a few areas of simulation criteria. So here are some guidelines to help you understand when to use one versus the other. First, particle size. If your particle size is less than 80 microns, a dispersed method may be the way to go. If less than 50 microns, then you would definitely want to go with a dispersed method. Number of particles is large, say more than a few million. It makes more sense to simulate them as a dispersed field. If you were interested in tracking individual particles, AcuSolve EDEM coupling is definitely what you would need. When it comes to particle shape, both methods support isometric particles, but only the coupling supports non-isometric particles. So, in summary, granular multiphase is an extension of Euler-Euler multiphase and needed when the volume fraction of dispersed solids is high, above 20%, within a carrier fluid. Particles are modeled as a continuum and assumed to be spherical or approximately spherical. Additional models for solid pressure and solid viscosity have been added, as well as models for particle-to-particle and particle-to-wall interactions. There are two drag models that are recommended for dense flow, the EMMS and GITISPOW. And all of this is available both from SimLab as well as HyperWorks CFD. The final new feature release for 2022 is the electric potential solver. With this feature, Altair AcuSolve continues its investment into electric thermal analysis capability. The feature solves for the thermal effects of a specified voltage drop or current, and the physics are based on the conservation of charge, and multiplier function control of the boundary conditions allows for simulating electric duty cycles. And this feature further expands AcuSolve's battery thermal simulation capability. So with this feature, a new material model component, the electrical resistivity model, is added to define the electrical resistivity of a solid in ohm meters. Two types are available in the SimLab interface: constant and as a linear function of temperature. Defining the resistivity as a function of temperature is the recommended method for improved accuracy. A reference temperature, a reference resistivity, and a linear temperature coefficient are required to define that relation. And the plot at the right here shows three linear temperature relations that vary by temperature coefficient. New output variables with this feature include electric potential in volts. Other names for this variable are electric field potential, potential drop, or electrostatic potential. The other new variables are current density in amperes per square meter, which gives the current through a cross-section of the conducting solid. Finally, the joule heat density in watts per cubic meter is the electric power per unit volume. So the electric potential solver, or joule heating, as it's also known, is available in SimLab for version 2022. To expose the setup options, users will create a flow solution. I just want to highlight that this is available in the flow solution, not the electromagnetics solution, which is right next to it, and activate heat transfer within that flow solution. So this will show the option to include electrical effects. Currents and voltages are specified on surfaces. And these surfaces should be attached to solid bodies through which the current will be calculated. And a ground voltage must be specified on the model somewhere. This example, we have a 1 amp fuse. Under steady load, we see in the upper right image that the temperature of the zinc fuse element is about 295 Kelvin. That's 22 Celsius or 71 Fahrenheit. The animation at the lower right simulates a surge condition where the maximum temperature of the fuse element reaches 421 Kelvin. The melt temperature of zinc is 693 Kelvin. This extra load is not enough to blow the fuse. So with AcuSolve's electric potential solver, the thermal effects of electrical inputs can be simulated based on the solution of the conservation of charge. Duty cycles can be simulated through multiplier functions on the electrical inputs. And this feature is available in the 2022 version of SimLab. So the installation packaging for Altair's CFD solvers is being separated into two. The previous HW-CFD solvers package will contain just the solvers themselves, AcuSolve, NanoFluidX, and UltraFluidX. The second package, which is called HW-CFD Solvers Help, will contain general documentation like HTML pages and PDF documents. Both packages are available for download from Altair One, and the Help installation now has its own Start menu icon after you install it. And when you click that, it takes you to the top level simulation, Altair simulation webpage. To access the AcuSolve content, you scroll down to the middle of the page to the section titled Altair CFD Solvers, and there you will find the link to AcuSolve. So feel free to bookmark this for more direct access. The tutorial models for HyperWorks CFD and HyperMesh are available for download by clicking a link within each tutorial help document. Within each tutorial, it points to a single link that contains a zip file of all of the tutorial files. SimLab tutorials and model files are available online from the SimLab Learning Center, but also can be downloaded by clicking the link within each tutorial. Validation cases, again, as one single zip file, can be downloaded from a link at the top of the validation section of the help. New tutorials for Euler-Euler multiphase, granular multiphase are now available in both HyperWorks CFD and SimLab. And the electric potential tutorial is available in SimLab. So 14 new tutorials have been converted to the SimLab interface. 7 of them are shown here: atmospheric boundary layer, the compressible flow, nuclear boiling, just to name a few. The other 7 are shown here, the bulk of which are the AcuSolve EDEM coupling options. In addition to tutorial cases, 4 more validation cases have been converted over to the SimLab interface as well, and they're listed here. Several improvements in addition to the main features have been added for version 2022 of AcuSolve. The first improvement is in handling high-speed rotating machinery in AcuSolve EDEM coupled simulations. The robustness of COSIM has been improved when large volume fraction non-spherical particles are involved. As a result, the solver stability has been improved without the need to add any additional parameters. And the larger time steps can likely be taken on the AcuSolve side as a result of this improvement. In addition to improving robustness, a bug related to accurately tracking solid volume fractions of particles in highly compressing or expanding meshes was found and fixed. These 2 issues improve the performance of AcuSolve EDEM coupled simulations with any type of mesh motion. Another enhancement is the ability for users to define their own lift and drag models for AcuSolve EDEM coupling through user-defined functions. This has been added to the lift model and the drag model definitions under the field interaction model command. Users are encouraged to test their functions for range and validity prior to running them in a simulation, because AcuSolve doesn't perform any bound or error checking other than syntax. The next enhancement is that the Ogden flavor of mesh motion control has been brought into the input deck. The previous ALE type, which is based on the mesh quality metric, or MQM, is still named ALE, and the new parameter is now ALE_Ogden. Users are encouraged to run the default MQM flavor first, and then try ALE_Ogden if severe distortion occurs with MQM. Microsoft Visual Studio support has been extended to version 2019 for all types of Visual Studio when compiling UDFs, and the location and version of the compiler are also now reported to the user. Topology optimization has been improved with respect to convergence speed and overall robustness. Porous zones are now supported with topology optimization, and lower viscosity fluids are now more precisely handled, allowing for simulations of higher Reynolds number flows. From a convenience standpoint, the user is now notified when any unsupported physics have been selected, or if no design volume has been specified. Some other bug fixes and updates are listed here. First, the default lift model for Euler-Euler and algebraic Eulerian has been set to none. An issue with conduction in thermal shells, which was allowing heat to leak out the ends of a thermal shell that was inside the model, has been fixed. We've updated the CUDA libraries for AcuSolve's GPU capability to 10.2. There was a bug with PQ curve input to fan component that has been fixed. Specifying pressure inlets with the human air model is now working correctly. And initialize Stokes now initializes the eddy viscosity field correctly. An issue with specifying nodal initial conditions by element set that was reported has been fixed, and ideal gas steady state runs have been improved as well. In the command reference manual, non-spherical lift and torque model information has been added under the field interaction model section. And in the programs reference manual, there's information about setting the number of threads for AcuPrep. And finally, hypermesh-based tutorials have been updated and now reference hypergraph for 2D plotting. Thank you for watching this webinar.